We had talked about chapter 6. We had started chapter 6 last time. Uh, we, we got through almost half of the chapter, but what I'm going to do is I'm going to quickly review what we did last time and then go over the new stuff. Okay? So we're interested in fluid flow, and the way you make fluid flow is by applying a pressure difference at the pipe, at the ends of the pipe. Okay? All right, so pressure is defined as force per unit area. Okay? So fluid will exert pressure. We will deal with the atmospheric pressure quite a bit, and so here were various units for atmospheric pressure. 1 atmosphere is in SI units, it's 10 to the power 5 pascals, Newton per meter squared. Okay? 1 atmosphere in pounds per square inch is about 15 pounds per square inch. 1 atmosphere in the column height of a mercury is 76 centimeters of mercury, or 760 millimeters of mercury. Okay? So you saw that. Now what this diagram illustrates is, let's say you apply a force of 15 pounds with a finger, and you apply a force of 15 pounds with a needle. Okay, this hurts more. Okay. The difference is that force is being applied over a smaller area, the pressure is greater. Okay, and a greater pressure will break the skin. Okay, so we saw that. The pressure, so the pressure at this level, the pressure at this point, you can think of this as the weight of this column of air all the way to space. Okay. And that pressure is, again, at this point it would be 1 atmosphere. And if you go to a certain height, let's say if you go about 5 miles up in the air, that column of air weighs half as much. So if you go up 5 miles, the pressure is about half an atmosphere. Okay? If you go all the way to the space, what is the pressure? Nothing, 0. Okay? So there's no more atmosphere weighing you down. Okay? Now, fluids exert pressure perpendicular to the surface. Okay, so no matter what the surface is, so if, for instance, the roof was like that, the pressure there would be in that direction, the pressure here would be in that direction. So fluids exert pressure perpendicular to a surface. Okay. The atmosphere is exerting a pressure here, so there's a force on the wall. Okay. And the force can be quite large. Like I said, so here's a calculation. The pressure on this wall is 10 to the power 6 newtons, and the mass of that is 10 to the power 10 newtons. That's roughly the weight of 10 school buses. The force on this wall due to the atmosphere is equal to 10 school buses. And the only reason this wall is not collapsing is because there's an equal and opposite pressure on the other side. Okay? Atmospheric pressure arises because of air molecules bouncing off. There are billions and billions of molecules bouncing off every second. And so these air molecules bouncing off are exerting a pressure on the wall. And the force that the air molecules exert on the walls are 15 pounds per square inch. That's atmospheric pressure. Okay? All right. So this formula, this is the ideal gas law that relates the volume, that relates the pressure, volume, and temperature of the gas. Okay, so N is the number of moles of gas. Okay. 1 mole of gas, you might have studied. 1 mole is equal to 6.023 times 10 to the 23 molecules. Okay, so this is something you'll study in chemistry. So for instance, if you take water So the atomic mass of oxygen is 16 atomic units. Atomic mass of hydrogen is 1 atomic units. So the mass of this molecule is 18 atomic units. And if you take 18 grams of water, you will have that 1 mole of water and that many molecules of water. Yep. 18 grams of water is about a half a mouthful of water. Okay, so every time you drink half a mouthful of water, you're drinking about 10 to the power of 24 molecules of water. Yeah. All right, what this formula tells you is the following. So if you go underwater, okay, the pressure decreases as you go deeper. Okay, so if you're at this depth, the pressure is due to the weight of this air column all the way to space, which is atmospheric pressure, and then the pressure due to this column of water. Okay, and so that's what this is giving you, the pressure at a depth. Okay, that's the atmospheric pressure, and that is the pressure due to the fluid. Okay, that is the density of the fluid, that's acceleration due to gravity, and that's the height or the depth to which you've gone down in the fluid. Okay. And in water, if you put in the numbers for water, density for water, if you go down 33 feet underwater, you get another atmosphere. So you have 1 atmosphere, 33 feet underwater, you have 2 atmospheres. 66 feet underwater, you have 3 atmospheres. Okay. All right, so that is the absolute pressure at that point. Okay. Oftentimes, you do not measure the absolute pressure. When you use a gauge to measure pressure, what you're measuring is gauge pressure. Okay. So gauge pressure, and it's named that way because that's the pressure. That's what most pressure gauges measure. It's the absolute pressure minus atmospheric pressure. So for instance, that's what, when you go fill air in your tires at a gas station, the gauge is measuring the actual pressure minus the atmospheric pressure. So in your tires, the gauge measures 30 psi. So this is 30 psi. So the actual pressure is 30 psi plus 15 psi, 45 psi. Okay? All right. So in a lot of our measurements, we measure gauge pressures in the health industry. So we shall use the convention that all pressures are gauge pressures unless otherwise specified. So whenever we tell you 120 millimeters of mercury, that's your what is it, systolic pressure, the high pressure, that's a gauge pressure. Okay? All right, what this diagram shows you is the following. So if you want the fluid to flow in this pipe, what you want is higher pressure on this end and lower pressure on this end. All right, so if you want this fluid to flow into the bloodstream, so here's the IV system. Okay, so let's say this is the needle. The high pressure in the highest pressure, let's say, in the bloodstream is 120 millimeters of mercury. So if you want this IV fluid to flow into the veins, this pressure has to be higher than the 120 millimeters. Okay. So if the IV bag is too low, this pressure won't be higher than that, and the IV fluid won't flow into the bloodstream. And so if that happens, all you have to do is raise this bag, make sure that the pressure here is higher than that, okay, and then the fluid will flow in. Okay. Now the pressure at this point, at the entrance of the needle, doesn't matter how this pipe is. Okay, all that matters is this height. Now, what we saw is how to fill an eyedropper. Okay. The air in the eyedropper at the beginning is at 1 atmosphere. There's 1 atmosphere, so this 1 atmosphere is not able to push in any fluid. So what you want to do is remove some of the air first and decrease the pressure in there in the eyedropper, and this higher pressure will push fluid in. So, and that's how you load an eyedropper. We saw the Pascal's law. The Pascal's law says that if you have an enclosed fluid, on an enclosed fluid, if you increase the pressure at any point by a certain amount, the pressure increases by the same amount everywhere in the fluid. Okay? So let's say if you increase the pressure at this point by 1/10 of an atmosphere, everywhere in the fluid, the pressure increases by 1/10 of a fluid. And what this is useful for is the following: if you have a fluid enclosed like this, and here's a small cylinder, a small diameter cylinder, you push on this piston, the pressure in the fluid will push outwards here. Okay, so you can apply a small force and get a large force out there. So the input force, with a small input force, you can get a large output force. Okay, well, how large an output force can you get? Okay, the output force is the area of the output cylinder divided by the area of the input cylinder. All right, so if this is a circular cylinder, area is given by pi r squared. Okay, so if this radius is 5 times this radius, the output area, 5 square is 25. The output area will be 25 times the input area. Okay, so if the input cylinder is like that and the output cylinder is like that, okay, 1 inch and 5 inch, the output force is 25 times the input force. So by applying a small input force, you can lift a heavy load. Okay, and this is what, so one of the applications is the dentist chair. The dentist is pumping, pushing with his pedal there and lifting the patient up. Okay? So you can see that with an input force of 50 newtons, you can get an output force of 1200 newtons. Okay. So an input force of 50 newtons is giving you output force of 1200 newtons. Okay, we saw the blood pressure measurement. Here's how it goes. Okay, so here's a blood vessel. There's the blood vessel. Okay, and the blood pressure is keeping the blood vessel open. Okay, when you measure the blood pressure, what you want to do is, when you want to measure the blood pressure, the higher, if you using a cuff, you can apply a pressure on the blood vessel. When the pressure applied by the cuff increases the highest blood pressure of the blood, the blood vessel collapses. Okay. And so again, the cuff is at the same level as the heart. You apply a pressure on the cuff and make the blood vessel collapse, and once the blood vessel collapses, all the blood flow is stopped, and you want to that's what you're doing with the stethoscope, monitoring the flow of blood. Once all the blood vessel collapses, there's no more blood flow and you don't hear the blood flowing. Okay, so you want to make sure that the cuff and the stethoscope is on this side, the downstream side, and you don't want the stethoscope on the upstream side. Okay, so that's the wrong placement of the stethoscope. You want it on the downstream side. Okay, so when you're measuring blood flow, this that is air that is transmitting the pressure. Okay, and when it's air transmitting the pressure, this gauge can be anywhere. When you're measuring spinal column pressure, it's a saline solution that's transmitting the pressure, and then it's important that the gauge be right at the level where you're measuring the pressure. You don't want the gauge there or there. Okay, so I don't know if you guys have dealt with that, but that's something you need to be aware of. A manometer, that's a device that measures blood pressure. It measures gauge pressure. Okay, so it gives you the actual pressure minus atmospheric pressure. Okay, so there's the air going to the cuff. Okay, and that is open to the atmosphere. Okay, so here's the atmospheric pressure plus the pressure of this column, and that's the pressure at this level. Okay, and that goes to the gauge, and it's only measuring this pressure. Okay, so the manometer is a device that measures gauge pressure. A barometer is a device that measures the actual pressure. This is perfect vacuum, and this column of mercury is balancing an equal column of air all the way to space. Okay, and so this will be 70. If this was mercury, this height of this, the height of this column would be 76 centimeters. Okay? And if bad weather is coming, if the pressure gets lower, the column in this mercury column would decrease. Okay. We saw that an aneurysm is a weakening of a blood vessel. When the blood vessel weakens in a local area, the pressure will make it bulge, and then the problem gets worse. Okay, so when the area increases, when you have a bulge, the area increases, and if the pressure is the same and the area increases, then you have a larger force acting on it. Okay, so you got the bulge to begin because the walls got weak, and then you're applying greater force. Okay, and so the problem gets worse. Okay. Now, we'll talk about this later in the chapter. There's another problem. When you have a bulge, you get turbulence in there. Turbulence decreases flow rate, and the reaction of your body is to increase the pressure, to increase flow rate back. So the problem gets worse and worse. The area is increased, your body's reaction is to increase the pressure because flow rate has decreased, and the force on the aneurysm gets larger and larger. Okay. So if you suspect that the patient has an aneurysm, you want to make sure that their pressure doesn't rise. Okay. So the buoyant force, if you immerse an object in a fluid, it will feel an upward force. Every object feels an upward force. Okay? And that is because the pressure at the top is smaller than the pressure at the bottom, and so there's a net upward force on the object. All right, well, so there's the force of gravity, that's the weight of the object, and there's the buoyant force. Now, if the buoyant force is equal to the weight, then the object won't sink. If the buoyant force is larger than the weight, the buoyant force will rise up. And if the weight is greater than the buoyant force, the object will sink. So for a rock, the weight is greater than the buoyant force, it'll sink. For a piece of wood, the buoyant force is greater than the weight, and then that'll rise up. Okay? For an object whose density is equal to the density of water, the buoyant force will equal the weight. Okay? And that object, if you put it underwater, it will neither sink nor float up. Yeah? Archimedes' principle tells you how large this buoyant force will be. Okay, so I'll write it as FB. The buoyant force is equal to the weight of the displaced fluid. So this object displaced that much fluid, and this force is equal to the weight of that much fluid. Okay, that's what Archimedes' principle says. Okay. When an object floats, its density is less than the density of the fluid. So the density of the object is less than the density of the fluid in which it's floating. Okay? And the fraction that is underwater or in the fluid is, this formula gives you that, the density of the object divided by the density of the fluid. So this is less than 1. Okay? And that's equal to the displaced volume divided by the volume of the entire object. Okay. So for an object to float, its density has to be less than the density of the fluid. Okay. All right, so essentially we got up to this point. So now we'll start the new stuff. Okay, so we will be interested in a fluid flowing in a pipe. So for instance, you want blood to flow in your blood vessels. Your blood is transporting nutrients and oxygen and bringing back toxins to wherever they need to go, and carbon dioxide and all that. All right. To make blood flow, to make a fluid flow, you have to have a higher pressure here and a lower pressure there. You have to have a pressure difference. Okay. Now, let's say you, in this pipe, you have maintained a certain pressure difference, and if you try and make water or honey flow, you know that more water will flow, more gallons of water will flow per minute. Okay, so honey has greater resistance. Okay, so what this formula tells you is this is the flow rate. Flow rate tells you how many gallons a minute are flowing, or how many liters a minute. The flow rate is the pressure difference divided by the resistance to flow. Greater the resistance to flow, smaller the flow rate. Okay, so for instance, we'll see a problem in a second. When you eat a meal, you want to increase flow rate by a factor of 5 to your digestive system. Okay, so how do you increase flow rate? If you want to increase the flow rate by a factor of 5, you can increase the pressure difference by a factor of 5. That's, your heart is having to work a lot harder. The easiest way to do is to change the resistance. Okay? And the resistance is given by this formula. See, the resistance is at 8 eta. This guy is the viscosity, eta, and L is the length of the pipe. Pi r to the power r is the radius of the pipe. So if you want to reduce resistance, the easiest thing to do is increase r, the radius of the pipe, dilate the pipe. Okay, so the best way to increase or decrease flow rate is to change the radius of the blood vessel. Okay? By increasing the radius, okay, so if you increase the radius, the resistance of the pipe decreases. Okay? And then the flow rate will increase. So keep that in mind. The best way the body controls flow rate is by dilating or constricting blood vessels. Okay. All right, so again, flow rate is the pressure difference divided by the resistance to flow. And so Poiseuille's law, so when blood flows in a nice laminar fashion, the resistance is given by Poiseuille's law, and resistance, like you saw in the formula before, is that pi r to the power 4. And when you put that formula in here, there's this formula. So this PDF conversion didn't work properly. Here is the correct pi r to the power 4, 8 eta L. Yeah. So in this formula, you can see that Okay, if you want to increase flow rate, the best thing to do is raise the radius, dilate the blood vessel, you increase the radius and you increase the flow rate. If you decrease the radius, you'll decrease the flow rate. Okay, you can't change the length of a blood vessel, you can't change the viscosity of the blood, so you can't control any of this. The only two things that you can control is the pressure difference or the radius of the blood vessel. Okay, and pressure difference, you're making your heart work harder. Okay, and you don't want to. The easier thing to do is to change the radius of the blood vessels. Now, good athletes, when they're exercising intensively, they do both. They increase the pressure a little, okay, but the payoff is not as much, and you dilate the blood vessels. Okay, the payoff is much higher there. Okay. Okay, and let me just illustrate this point. So let's say if you increase the blood, so what I've done is I've increased the radius by 10%. Okay, that's what that means. And so 1.1 to the power 4, do that on your calculator. I'll do it for you guys on the calculator. So 1.1 to the power 4. Okay, is equal to 1.46 r to the power 4. Okay, by increasing the radius by 10%, you have increased flow rate by 50%. Okay, so that's what that number means. Okay. So again, controlling flow rate is done most easily by changing the radius of the blood vessel. Okay. And so that's what this problem says. Okay, when a person eats a large meal, blood flow in the digestive system is increased by dilating blood vessels supplying the system. So by what factor must the flow regulating vessel dilate to increase flow rate from 1 liter a minute to 5 liters a minute? So you're increasing the flow rate by a factor of 5. And this problem goes through the thing, and what it shows is if you dilate the blood vessel by 50%, so you increase it to 1.5, its original radius, the flow rate has increased by 500%. Okay. During strenuous exercise, to increase flow rate, the human body does both in the circulatory system. The blood pressure increases and the major blood supplying arteries dilate. Okay, so again, let me fix this. Q is P2 minus P1 pi r to the power 4 8 eta L. Okay, so what we are saying here is, okay, to increase flow rate, the body increases the blood pressure and dilates the blood vessel. Okay, now here's the deal. If you increase the blood pressure by 10%, you go from 120 millimeters to 130 millimeters, the flow rate only increased by 10%. You increase the radius by 10%, the flow rate increased by 50%. You saw that a second ago. Okay? All right. Okay, what this slide shows you is the following. Okay, so at the needle where the blood is entering, you see the radius is very small. At the needle, the radius is very small. The resistance is very high. Okay, at the needle, the resistance is very high, and so delta P is the pressure difference between the two ends of the needle, and this is small. Okay, since the resistance is high, the flow rate is small. Okay, so you have a small drip going. And if you want to slow that down even more, what you do is you put a clamp somewhere here. And by doing a clamp, there's a large pressure drop there. The pressure drop across the needle decreases. The resistance is the same. and the flow rate is even further decreased. All right, anyway, what you want to remember is, and you guys intuitively know this, the thinner the pipe, the slower the flow rate, and that's because the thinner the pipe, smaller the radius, higher the resistance, slower the flow rate. Okay. All right, so here's the flow rate in a fluid. You're seeing this equation 100 times. That's the pressure difference, and that's the resistance to flow. Okay. Now, so here's a fluid flowing. This is laminar flow. Okay. So if you put a little drop of ink there and a little drop of ink, in a laminar flow, they would flow parallel. This here is turbulent flow. Soon as the flow becomes turbulent, the resistance goes up. Okay. So this has higher resistance. Laminar flow has a lower resistance. Okay. Well, if the resistance goes up, to maintain the same flow rate, you have to apply higher pressure. You have to work harder. Okay. So you don't want turbulent flow. So for instance, if flow becomes turbulent in your blood vessels, your heart would have to work harder to maintain a blood flow. Okay? So turbulence is not good. It costs you money. Okay? All right, so we're going to talk about turbulence now. Okay? When it's laminar flow like this, by the way, this formula works for the resistance. Okay, 8 eta L pi r to the power 4. When the flow is turbulent, this formula doesn't work. Okay, it's greater than that. So this is Poiseuille's law, and this works only for laminar flow. Okay. Anyway, all we want to remember is when you have turbulent flow, resistance increases and the flow rate decreases. You would have to increase the pressure to maintain flow rate. Okay. Turbulence has many causes: sharp bends and partial obstructions. So when you have plaque deposited in blood vessels, you'd have turbulence downstream. Okay. It's often possible to hear turbulent flow. So if you have turbulent flow happening in a pipe, you can hear it. Okay, so when you hear water running somewhere in your home, that's because there's turbulence. Okay, that's what you're hearing. Heart murmurs are sounds produced by turbulent flow through a defective heart valve or hole between heart chambers. An aneurysm can also cause audible turbulence. Okay? So if you have an aneurysm, the shape causes turbulence flow, and you can hear that. Okay? Turbulent flow always presents more resistance. Okay? So whenever there's turbulence, resistance increases, flow rate decreases. Okay? When this gets larger, flow rate decreases. Okay, in the case of an aneurysm, the body, because the resistance increases because of turbulence, the flow rate has decreased, and so what the body does is it increases pressure. In the case of an aneurysm, the body may respond by increasing blood pressure to maintain normal flow rate. Unfortunately, increased pressure only worsens the aneurysm. Okay? The aneurysm was because there was a weakening in the blood vessel, and then you push harder on the walls, you're eventually going to burst it. Okay. So modern cars are designed to cause minimal turbulence to avoid extra resistance. Okay, so your car is aerodynamically shaped because when your car moves in the air, what you want is laminar flow there. If you have turbulence behind, this causes more resistance, you're using more gas. Okay, so the aerodynamic shape is to avoid this turbulence. But the thing is, the faster you go, the harder, the more turbulence you will have, and the more resistance you will encounter. Okay. All right, so I hope you understand that turbulence costs you. Okay. Why does turbulence cost you? Because there's more resistance to the flow. Okay. Or if you're traveling through a fluid, for instance, if your car is traveling through a fluid, there's more drag forces on you. Okay. So aircraft, ships, and submarines are similarly designed, and the shape of the fastest birds in sea life are such as to create very little turbulence. Okay, so why are you doing that? So it doesn't cost you as much to travel. Okay? Right, so here's laminar flow. This is what you want. And as you increase the speed of the fluid, eventually you transition to turbulent flow. Okay, so the faster you travel, and if there are irregularities in the tube you're traveling, turbulence will set in. Turbulence is also caused by large fluid speeds. In small blood vessels, especially capillaries, interaction of the cells with vessel walls causes turbulence. Okay. In larger blood vessels, flow is approximately laminar, and Poiseuille's law applies quite well. Okay. So when you have turbulent flow, you cannot give it's very difficult to calculate the resistance. So we don't have a formula for the resistance. Okay. There's the flow rate, pressure difference divided by the resistance. Okay. So by the way, fuel consumption in cars, driving at about 50 miles to below 50 miles is less because turbulence has not set up. When you drive faster than 50 miles an hour, as you increase the speed, resistance increases and your fuel consumption increases. Okay. So this is the drag force when an object is traveling in a fluid. Again, so again, this is for a non-turbulent flow. All right, so so we're seeing that turbulence is not good because it causes higher resistance, and to maintain blood flow, you have to work harder. Okay, so one of the things we're interested in is when does turbulence set in? Okay, so what this is illustrating is this is let's say a spear moving through a fluid in this direction, and we want to know when does turbulence set in. Now, if turbulence set in, then you would have to work harder to move, okay? And you want to avoid that, so you would want to move at its speeds lower than that, okay? So there's something called a Reynolds number that tells you when you transition from laminar flow to turbulent flow. Okay, so you can see this is the Reynolds number, and it's just a dimensionless number, and as long as the Reynolds number is smaller than that, you have laminar flow, okay? And you see, as you move faster, the Reynolds number is increasing and turbulence is setting in. And for these Reynolds number, the flow is turbulent. The Reynolds number is given by this. Rho is the density of the fluid you're moving in. D is the diameter of the object. Okay, so if this was let's say a car, that would be that dimension. V is the speed of the car moving through the fluid, and eta is the viscosity of the fluid. So you see, the faster you're moving, the higher the Reynolds number. Okay, and so the Reynolds number. Okay. So depending on tube geometry, the onset of turbulent flow occurs when the Reynolds number is greater than about 2,500. Okay. So when this number is greater than 2,500, then turbulence will set in and resistance increases. So again, Reynolds number is density, diameter, average velocity divided by that. Okay, you see larger velocities, larger objects, and lower viscosity contribute to larger Reynolds numbers. All right, now we're looking at a fluid moving in a pipe. All right, if I toss an object up, so let's say I toss this keychain up, what happens to the speed of the keychain as it rises up? I'm sorry? So it slows down, so it decreases, okay? So, all right, so let's do the following first. So here's a pipe, and this pipe widens. Okay. Now it's at the same level. Okay, we'll have fluid flowing in here. And let's say 1 gallon a minute is flowing in here in this pipe. This pipe has no leaks. How many gallons a minute is flowing out? 1 gallon. The same amount of fluid is flowing in. Okay, this is the flow rate. The flow rate is the area of cross-section of the pipe times the speed at which it's flowing. A2, V2. Okay, flow rate is, the volume flow rate is the area of cross-section of the pipe and the speed of the fluid at that point. This is, so flow rate, whatever is flowing in is flowing out. So if the pipe gets wider, the speed of the fluid decreases. Okay, if the pipe gets wider, if the pipe gets wider, the speed decreases. All right, so one of the applications is the following. So when blood comes out of your heart, it's flowing quite fast, about 2 feet a second or something like that. Okay. Now, if the blood flew by that speed near your cells, you won't be able to absorb anything. You wouldn't be able to exchange any of the oxygen or nutrients and stuff like that. So how do you slow down the blood near the cells? Did you guys understand what I'm saying? So all right, so out of the heart, the blood is flowing maybe about, again, let's say 2 feet a second. And you don't want the blood flying by the cells like that. How do you slow this blood near the cells? You just saw the flow rate. The flow rate is area of cross-section times the velocity, okay? So if you want to decrease the velocity, you have to increase the area. Well, you don't want a big blood vessel going by the cell. Okay, you can't accommodate it. So what do? You break it into tiny capillaries. And you increase the area. And that's the function of the capillaries. Okay, you're increasing the cross-sectional area tremendously and decreasing the blood flow rate. Okay? And the blood flow at the capillaries is about 1 millimeter a second. And at that speed, now you can exchange nutrients and oxygen and all that. Okay? So that's the equation of continuity. Okay. So this gives you the flow rate, and when you want to decrease the flow rate, you want to decrease the speed of the fluid, what you want to do is increase the area of cross-section. You can do it by widening the pipe or breaking the pipe into smaller pipes, and the total area adds up. Okay. All right. Now, so when fluid flows through a pipe whose area of cross-section is changing, you saw that the speed is changing, And as it rises, the pressure also decreases. Okay. Mr. Bernoulli studied all of that. Okay. So he studied fluid flow, flowing in pipes where the area of cross section is changing, the level height of the fluid is changing, and all that. Okay, and he came up with this principle. And before I show you that, look at this pipe. So here is fluid flowing in this pipe, and this is measuring the pressure. This is measuring velocity and pressure. Okay, so here is the pipe, and when the area decreases, the fluid has to flow faster. When the velocity increases, the pressure decreases. Okay, so in a faster moving fluid, the pressure decreases. You want to remember that. Okay, so for instance, here's an airfoil. This is how planes work. This is the cross section of a wing, and when the plane is traveling in this direction, air is flowing over the wing like that. See, this air has to travel, because of the shape of the wing, this air has to travel a larger distance than this air. So this guy, velocity at the top is greater than the velocity at the bottom. Whenever fluid flows faster, the pressure is lower. Pressure is higher here. And that is what gives you the lift. Higher pressure gives you the lift. Okay? So you can see that that's what's illustrated here. When the pipe is constricted, fluid is flowing faster, and the pressure is lower. All right, so we'll see applications of that. Okay. Pressure in a fluid varies as it moves through a region where its speed and or elevation changes. The relationship between fluid speed, pressure, and elevation was first derived by Mr. Bernoulli. Okay. And here is the formula. So what he says is the following. Okay, so you have a fluid moving. You can go to any location, the pressure at that location, plus this is the density of the fluid, this is the kinetic energy of fluid per unit volume, this is the potential energy per unit volume. The sum of those three terms is constant. The sum of those three terms at any location is equal to the sum of those three terms at any other location. Okay. This is the pressure. This is kinetic energy per unit volume. That is potential energy per unit volume. Okay. You want to pay attention to this. This is important. The sum of those three terms at any location in the fluid is equal to the sum of those three terms at any other location. All right. So let me do a special case. Let's say where this guy, the elevation is the same. Let's say these two terms are equal. So, okay, I will write it down here. P1 plus 1/2 rho V1 square plus rho GY1 equal to P2 Okay, for simplicity, we'll consider the case where y1 is equal to y2, so these terms cancel. Okay, now let's see this. Okay, if the speed increases, if the speed is greater than at location 1, so if this term increases, pressure has to decrease. Okay, so anytime fluid flows faster, the pressure decreases. And that's what we were talking about here. So to make a plane fly, all you have to do is shape the wing like that. That way you're forcing the air to flow faster there. The pressure decreases and you get a lifting force. And this lifting force is equal to the pressure difference times the area of the wing. And that's the area of the wing. Okay, so now you can understand stuff. Okay, how much lift do you want? What do you want? The plane not to fall off from the sky, right? You want a lift force equal to the weight of the plane. So the bigger the plane, you want a larger wing area. Yeah. All right, so again, what I want you to remember is if a fluid flows faster, the pressure at that location is lower. Okay? So when the fluid flows faster, the pressure there decreases. By the way, the flow must be non-turbulent and irrotational. Okay. So here is a so here we'll use that formula. Okay, so when a fluid flows faster, pressure drops. Okay, so we use this idea in several places. Okay, so here's a perfume bottle. When you spritz perfume or when you're using what is this? What is it called? A sprayer, as any kind of sprayer. Okay, so here's what's happening. Here's perfume, and there's a tube in the perfume. All you do is blow air across this tube. When you blow air across the tube, whenever air flows, the pressure there has dropped, and the atmospheric pressure will push perfume up, and that perfume gets caught in the airstream, and that gets blown up. Okay. Did you guys understand that? So again, what you want to do is decrease the pressure there so this atmospheric pressure can blow up the perfume. So all you have to do is blow air across there. Okay. So
is it the
atmospheric
pressure and the pressure of the fluid that will push the perfume up?
All right, so I will draw a bigger diagram here. We'll keep it simple. Okay. So here's the perfume bottle. There's perfume. We'll put a tube in there. Okay. There's atmospheric pressure. So what you're doing is you're blowing air across this tube. There the pressure becomes low. And this atmospheric pressure will push the perfume up the tube because the pressure there is low. I'm sorry? Yeah, it's like a dropper. Mm-hmm. So as soon as you stop blowing across there, the pressure goes back to atmospheric pressure, and now perfume won't rise. Atmospheric pressure, the fluid will be there. Okay? All right. You might have used a Bunsen burner in a chemistry lab. So this is the natural gas that's flowing in at a speed. And as this natural gas, what do you need to burn anything?
Air.
You need oxygen. Okay. And so when this natural gas is flowing, you have an opening here, the pressure dropped, and air flows in. So you have a constant airflow. And that's a safety issue too. You don't want a natural gas leak in the lab. Okay. So as long as gas is flowing, you'll have air flowing in, and it'll keep burning. Okay. Here's another case of entrainment. Okay, so you blow air. Okay, or this could be you blowing air, and water is getting caught here. Okay, so here's maybe you can make a humidifier work that way. Okay, humidify the air. Automobile carburetors entrain gasoline into an air in a venturi tube. Okay. So what is entrainment? When a fluid is flowing, the pressure in the fluid is dropped, and because the pressure in that fluid is dropped, you can entrain another fluid in that flow. Okay, you can insert another fluid in that flow. Okay, and that's what you're doing. So you're mixing two fluids. Okay, so you're taking advantage of this fact. Whenever a fluid moves fast, the pressure in that fluid has dropped. Okay? Whenever a fluid moves fast, the pressure in that fluid has dropped.
In the same fluid?
Yeah, in that fluid. Okay.
You're saying if it moves fast.
Okay, so here. So here's.
How about the entrainment occurs?
Okay, so if you want another fluid to go from here to there, what needs to be true? At this point, the fluid pressure needs to be high, and this point, the fluid pressure needs to be low. Okay, so let's say, for some crazy reason, let's say this is a plane flying, or whatever. Air is flowing faster here, and now you can insert another fluid here because the pressure here is low, and if the pressure is high, that fluid will flow in here.
So the second fluid has to be higher or
The second fluid, yeah, it'll be the pressure.
stronger
The pressure is higher here and pressure is lower here. Let's go back to this perfume bottle. Okay, so here the pressure is higher, which is atmospheric pressure. And if you lower the pressure here, this fluid will flow up there. And that's what's happening. How do you lower the pressure here? By blowing air across there. And so this perfume was inserted in the airflow. Okay? And that's called entrainment. Entrainment of perfume into the airflow. All right, so again, what is the deal? If the velocity of the fluid is higher, the pressure is lower. Okay? So here's a smart fella that uses this fact. Okay, so here's his burrow, and what he knows is at higher elevation, air flows at a higher speed. Okay, so this guy has natural air conditioning. This burrow opening is at a higher elevation, the air is flowing faster, the pressure is lower here. At this elevation, the fluid is flowing at slower speed, the pressure is high. Pressure is high, pressure is low. And so, this pressure difference drives air like that. And you have a continuous airflow. Yep. So that's how they build the burrows. Now, if those two openings were at the same level, then you wouldn't have this airflow. Okay. So, nature knows physics, and it uses it to solve its problems. Okay. All right. Now we'll talk about cohesion and adhesion. Okay. Cohesion is the force between two similar molecules. So here's water molecule, here's a water molecule, here's a water molecule. The force, attractive force, if they're too close to each other, they'll repel each other. But if you have above a certain distance, they will attract each other. Okay. This is called a cohesive force. The water molecule will also be attracted to the table, and this is called an adhesive force. Okay, So when two dissimilar molecules attract each other, that's an adhesive force. When similar molecules attract each other, it's called a cohesive force. All right, so now you might have occasions where the cohesive force is greater than adhesive force. The adhesive force will depend on what kind of surface you're sitting on. Or the adhesive force can be greater than cohesive force. Okay, so again, cohesive forces between like molecules, and adhesive forces between unlike molecules. Okay, so for instance here, this shows you okay, so this is mercury, okay, and these are capillary tubes, and this is water in capillary tubes. Okay, water is attracted to glass. Okay, there in the case of water, the adhesive force is greater than cohesive force. In the case of mercury, the cohesive force, that is the force between molecules of mercury, is greater than the force between mercury and glass. Okay, so here's the result. Because the adhesive force is greater, in the capillary, water rises, and in a capillary, the mercury is depressed because adhesive forces are greater. Okay. In a water, the water rises because the meniscus is like that, and for mercury, the meniscus is like this, pulling down the mercury. Okay. So that's the kind of stuff we'll talk about. Okay, again, okay, so we are talking about cohesion and adhesion. Cohesion is forces between like molecules. Adhesion is forces between unlike molecules. Okay, forces between molecules can be either attractive or repulsive. The forces are repulsive when the molecule gets very close together, and otherwise attractive. Okay, so here is the force. The force, when the force is positive, that's repulsive. This is attractive force. So when the molecules are further apart than that, the force gets attractive, and at this distance, the attractive force is the greatest. That's what this graph is showing you. Okay? The attractive part of the force is responsible for numerous phenomena, among which are surface tension, capillary action, and fluid viscosity. Surface tension is, okay, so this phenomenon is responsible for surface tension. Look at this bug walking on the surface of water. Here's a pin floating on surface of water. Have you guys ever seen this?
Above, but not a paperclip.
What's that?
Seen it above, but not a paperclip.
Okay. Maybe next time I'll bring it. I can make a needle float on a thing. Have you guys seen that? Okay. You've seen a needle floating on? Okay. All right, so this is due to surface tension. Okay, so let me tell you how surface tension arises. Okay. And I think after this, we'll stop because I don't want to rush through the slides. And let's see. Okay, so here is a water molecule inside a cup of water. This water molecule is this water molecule is attracted by this guy. It's attracted by this guy in this direction, attracted by this guy in that direction, attracted by this guy in that direction. Okay, so now I'm going to draw all the forces. He's attracted by that guy, that guy, that guy, that guy. What is the net force on that guy, on this water molecule? What is the net force on him? 0. Very good. Okay. What's that?
I was going to say that too.
Wasn't sure.
Yep. All right, so if you're inside, if you're living inside, the net force on you is 0. Let's get to the surface, okay? All right, so let's look at a water molecule on the surface. Okay, what is this guy doing to him? He's pulling him to the right, this guy's pulling him to the left, this guy's pulling him. Okay, so now I'll draw forces on him. There's the force, there's the force, there's the force. What's the net force on the molecule on the surface?
Will it be equal?
Okay. This force is canceling that force, but this force is not being balanced. So every water molecule on the surface is being pulled in. Well, why isn't it going in? Well, there's no room. So it's under tension. Every water molecule is being pulled into the surface. Okay. He doesn't want to be there, but he has to be there because there's no room inside. Okay.
So what pulls the water molecule down?
The other molecules are pulling him down.
Other molecules?
Yeah.
Okay.
So a surface of a liquid is like a stretch rubber sheet. Okay? And it takes energy to put water molecules on the surface. Okay? Because you're pulling down, it's like, it's a spring. Think of a spring. If you stretch a spring, that spring is pulling you down. So it's being pulled down. Like chapter 5. So you have to, it costs you energy to put water on the surface. Okay, so you want to minimize the surface of a drop of water. That's why a sphere has a minimum surface. A sphere, in a sphere, there would be the least amount of water molecules on the surface. That's why when you see tiny raindrops, when a raindrop falls, what is the shape of a raindrop? A sphere. Okay? That way there are a minimum number of water molecules on the surface. Okay, so the surface of a water is like a surface under tension. Think of a rubber sheet. And that's what allows a bug to walk on water. So I'm going to draw a cross section. Here's the surface of the water. And now I'm going to draw the bug like a point. And this tension is balancing the weight. Okay? So this component of the tension is canceling, but this component of the tension is supporting the weight of the bug. Okay, so that's surface tension because there's an unbalanced force on every molecule on the surface. Okay? And so all surfaces are under tension. If you want to sink, you have to break the surface and get inside the water, and then you'll sink. Okay? All right, so this is what we're going to learn next time. I got all right, let me get to this slide and then we'll quit. Okay, so cohesion and adhesion. Cohesion is the force between like molecules. Adhesion is the force between unlike molecules. And this graph shows you when the molecules are this close together, the force, less than this close together, the force is repulsive. When they go, when the molecules are further than this distance, the force becomes attractive. And at this distance, the attraction force is the greatest. Okay, so surface tension arises because of this. A molecule, inside molecule, the net force on it is 0. A molecule on the surface, there's a net force there. So to put a molecule on the surface, it costs you energy. Okay, it's like stretching a spring to keep a molecule on the surface. Okay, so you want to spend the minimum amount of energy. So you want as few molecules as possible on the surface. So when you take a liquid drop, I don't know if you've seen mercury drops when the thermometer breaks. In mercury, the forces are very strong. So mercury, little droplets of mercury will be perfect spears. A drop of water, if it gets too large, can flatten out. Tiny drops of water will always be spherical. A drop of water falling will always be spherical. Okay? Smaller the drop, more spherical it will be, because it costs you to put a water molecule on the surface. Okay. All right, we'll stop here and we'll start again from here next time.